good afternoon, good evening. We're starting the second day of DecisionCAMP, and we started with a very interesting presentation from Peter Voss, who is really devoted his life to AI, or to be exact, AGI. And Peter, he is trying to bring human-level AI to the world. And he concentrates on real understanding beyond statistical methods. And Peter today will share his view on how in our new reality we may return to the original vision of AI, building machines that can think, learn, and reason the way humans do. And without any delay, I would happy welcome Peter, and we're looking forward to your presentation.
Thank you, Jacob. Yeah, exactly. That's right. It's AGI is really going back to the original vision of AI, when the term was coined 69 years ago now. The original idea was to build machines that can think and learn the way humans do, interactively and conceptually and so on. But then, of course, it turned out to be a really hard problem. So the field of AI really turned into the field of narrow AI to solve one particular problem at a time. And importantly, using really the human intelligence to solve a particular problem, like, playing chess or whatever. So in 2002, I got together with a few other people, and we believed that we should, time was ripe to get back to the original dream of pursuing thinking machines. And three of us actually coined the term artificial general intelligence, and we wrote a book on the topic. And I've been working on that, well, from before that to now, to try and make AGI happen, to have true human level intelligence. So I think the general consensus that AGI, when we achieve it, will be a really, really big deal, bigger than electricity. It will really change things tremendously. And I think it'll be fantastic for humanity. I think it'll really help humanity flourish. For example, imagine having one AI that can teach itself to be a PhD level, say, cancer researcher. And I said teach itself, the way a human does, by hitting the books, by learning, and interactively doing that. And so you now have one PhD level cancer researcher. You can now make 1 million copies of that, or however many, and you have 1 million PhD level researchers chipping away at the problem. So just imagine how much faster we'll make progress on the difficult problems that are facing us, in medicine and energy, like battery density, materials, pollution, and even governance, and how we run our society, by having essentially massively more brain power that we can apply to these difficult problems. Now, another very obvious area that AGI can help is dramatically reducing the costs of goods and services by being able to automate things. So that people talk about radical abundance, where really there'll be dramatic reduction, because human labor is really for many industries, it's by far the biggest cost of producing goods and services. So through automation, we'll be able to dramatically reduce them once we have true human level intelligence. Now, the third area that I'd like to highlight here is, I think, maybe the most important one even, and I call that a personal assistant. The reason I use personal multiple times is there are really different meanings of personal that I think apply to that. The first personal in here is that I believe we should each have our own, high-level AI that we own. So it's personal, it's ours. It serves our agenda, not some mega corporations. The second personal is that it's hyper-personalized to us. So it'll learn our history, our goals, our wishes, who we interact with, what our values are and so on. And the third personal is the issue of privacy, that we'll be able to control what it shares with whom and when. And I see that as a tremendous help for individuals, for each of us, to have this sort of trusted assistant that can really help us think things through and make better decisions. It's a little bit like an angel on your shoulder that can help you avoid making bad decisions that you regret. That's apart from doing some of the dirty work like dealing with insurance companies and government and so on that can take care of that. There's another way of looking at this personal, really deeply interactive personal AI that you have. It's almost like an exocortex. It's like an extension of your own brain, of your own mind. So I think that'll be tremendous for people to have that assistant to help us think things through better. Now, the other thing to kind of just remind ourselves of is having computers do a lot of these things like research or doing tasks. They inherently have benefits apart from just being potentially significantly cheaper than human labor. They also are able to collaborate and share information much better than humans would. You don't have egos getting in the way. They can really share insights and knowledge that they gain with each other much more easily than humans can. So that's a tremendous advantage. They can work 24/7 without getting tired, at full concentration, and probably quite a bit faster than we can. They also don't have certain distractions that we as humans tend to have. I mean, nice distractions. So they really focus on the cognitive work that they are tasked with. And then finally they have potentially photographic memory for everything they come across. They have instantaneous access to all of the information in the world just by essentially thinking about it. And they're also much better at logical thinking than we are. For humans, we are really not that good at logical thinking, a lot of fallacies that we fall prey to. And, rationality is really an evolutionary afterthought, whereas for AI, it will be, a core ability of an AI to do that. So, I want to just contrast that with a lot of the confusion that's out there, people talking about AGI. So like Sam Altman saying, oh, we'll have AGI soon, but it's not going to be a big deal. Well, either he doesn't understand AGI or he's badly abusing the term. And, maybe he's saying it to raise money or whatever. But, it's kind of annoying that people abuse a term like that actually has quite a clear meaning. So with AGI, what are some of the side benefits? And I already mentioned a few, so I'll go through a few other things of why I believe AGI will be so tremendously beneficial to humans. And one of them is, of course, computing power itself will be able to improve with much more efficient algorithms, using less power, being more powerful. Whatever benefits quantum computers can bring us. So there'll be inherently a rapid increase in computing power. Energy, I've mentioned, being able to design better batteries, pollution control and so on. Nanotechnology, we've for decades we've been dreaming about having these nanobots that can go into our bloodstream, into our bodies, and repair things and so on. It's technically feasible to do that. Actually, there's extensive research that's been done and designs that have been done, but to actually implement it is really quite hard, and expensive. So AGI again will help us to accelerate that kind of development and create much better materials for airplanes, rockets, cars, whatever, that are much stronger yet lighter, diamondoid materials and so on. So there's a lot that can actually be done in material science. In the medical front, well, I focused on that already. Obviously, conquering diseases, reversing aging potentially, organ replacements, and neural implants. All of those technologies can be accelerated significantly. Food creation, more efficient food creation, and potentially being able to create foods that taste as good as we want them to taste, but are also nutritious if you can really engineer things better. Lastly, I just quickly want to talk about what I think will be a really important impact is to have the brain power to be able to come up with better philosophy, philosophy about how we know what's right or wrong, or how to govern things. And I just want to highlight a philosophical movement that was around in the late 90s, early 2000s, called Extropy, and had a lot of these kind of ideas bundled together, integrated in I think, a very nice way. It's basically a pro-reason, pro-science, and a proactive optimism that basically we can have a better world, but it's not going to be automatic. We need to work at it. It's also about personal ownership, but personal responsibility. So I think having those kind of helping us think through rationally of what is right and wrong and what kind of governance makes sense. I think, again, AGI can help us think things through better. So if AGI is so beneficial, how do we get there, and how soon can we get there? So the next section I want to talk about is large language models, I believe, are not going to get us there. In fact, I agree with Jan LeCun's statement here that large language models are an off-ramp to AGI. They're a distraction, a dead end. So he puts it quite forcefully, and I would actually agree with that. But even Demis Hassabis, CEO of Google DeepMind, says that statistical systems are not going to get us there, not by a long shot. He said, actually, so that new breakthroughs are needed to do that. So I think there's consensus growing on that view. Now, what the alternative is, I think there is little clarity generally. So I'll spend a bit more time going through the inherent limitations, and obviously some are being tweaked and addressed to some extent, but I believe there are some really fundamental limitations. So the hallucinations, that it always needs a human in the loop. I mean, even the latest models, what makes them powerful is the human in the loop, the human evaluation of saying, the prompt engineering and evaluating and saying, well, yes, this model can do this, and no, the answer doesn't really make sense, and so on. I think a really big issue is that they cannot learn in real time. And I actually was a co-author on a white paper where we reviewed the recent research in ongoing learning on large language models. And we surveyed more than 200 papers that are referenced in my white paper. And not a single research paper actually addressed the issue of updating the core model in real time. Basically, it can't be done. So you can, add external things, you can retrain the system, but you cannot learn incrementally. And if you try to retrain the system, you also suffer or risk catastrophic forgetting. It's a black box, not audible. And so this is something obviously in this community that's going to resonate really well, that you really don't know how the system comes to certain conclusions and why it does certain things and gives certain answers. It has limited understanding and no metacognition. Okay, there's an argument now that with the latest models that are sort of try to think about their own thinking, or at least feed back their results to kind of make them try harder to come up with the right answer. But I think there's a lot of evidence that there really is very limited understanding, that they are not grounded in reality, and to a large extent they don't know what they don't know. And the last thing is, which really to me is maybe the single biggest thing, is they just extremely, extremely expensive, and we're running out of data. And the whole thing of the expense is becoming kind of so absurd. And I'll come show a few quotes later on that. But I do want to sort of just reinforce what those limitations are and why they are there. I mean, GPT already provides a good clue. They are generative. They make up stuff. They literally predict the next words with statistical variations, and so they create answers from the massive amounts of data that they're trained on, tens of trillions of tokens nowadays, good, bad, and ugly, which came from wherever the data came from, Twitter or wherever. And they don't really know what's good and bad and ugly. Now, the P is pre-trained. So, they are read-only. Once the model is built, the model is not updated until they train a new model. And that's part of the problem that you have. You spend hundreds of millions of dollars training a model, you then use it for a while, and as you get more training data or as the technology improves, 6 months later, you throw that all away. Hundreds of millions or billions even, they're thrown away. And the T stands for transformers, which of course is the breakthrough technology that came about, I think it's 7-8 years ago, or maybe more, that really makes these large language models so incredibly powerful, on the one hand, that they can do these magical things of summarizing, idea generation, and better translation and whatnot. I mean, they are really quite magical in what you can achieve with massive amounts of data and massive amounts of computing power. But the transformer technology, which really I don't see anybody breaking out of in large language models, inherently commits you to backpropagation, which inherently means it's bulk training. You need to have all of your training data available up front, and you need to number crunch it, millions of times to converge to the model that you have. So that really ties you into the pre-training read-only mode. And people trying to overcome the limitations of large language models basically, have layers of human-crafted fixes, fine tuning and having a bigger buffer and basically prompt engineering and so on, and having whatever protection guardrails that you have. But at a certain point, you kind of wonder the amount of engineering that surrounds a large language model, whether it isn't the tail wagging the dog, and whether there isn't whether you actually how much you need the large language model, or whether there isn't better technology to solve a particular problem. So I'll finish off by just showing how absurd, in my mind, the cost expectations are. I don't care if we burn 50 billion or 500 billion a year. These frontier models will cost $100 billion to build. Sam Altman seeking 7 trillion to achieve AGI. These are just absurd numbers. The amount of computing power, electricity that's required to do that. And here I'm contrasting it to our brain. I mean, if you go back to first principles, our brain uses something like 20 watts of power, not 20 gigawatts or something. A child can learn large language and reasoning, rudimentary language and reasoning, with probably a few million words that they're exposed to. Okay, they're also exposed to other stimuli, and I'll touch on that a little bit later. But, it's not tens of trillions of words. There's a huge difference between tens of trillions versus, a few million, and 20 watts versus the amount of power required to build these large language models. So what's the solution? So where people are looking is, neurosymbolic. Can we somehow combine the power of large language models, the statistical version, with some kind of rule-based system? The analogy there is Daniel Kahneman's System 1, System 2, System 1 being the fast thinking, the automatic thinking, statistical thinking, and System 2 being the deliberate, more logical, procedural thinking. So is that a solution? I would say yes and no. There are problems that in our brain, the way System 1 and System 2 work is they are not two completely different parts of our brain. They are totally integrated. The knowledge representation is uniform. There's one knowledge representation. You also need, as far as the logic part of the system is concerned, you really need vector encoding. You need to be able to have concepts all the way up, and concepts basically need to be, call them fuzzy in that sense. So you can't just have a formal logic alone. We know the limitations of formal logic by itself. And then, of course, the real-time learning. As long as you have large language models, you're not going to have real-time learning and of being able to update the core model. And that's key. If, for example, as a scientist, just to use a clear example, as a scientist, you get news that a particular paper that was maybe crucial to your research has been withdrawn. It changes lots of things in the way you think about it. There's a major update of the model. But even in everyday usage, as a programmer, you talk to a customer, you understand their requirements, you need to learn new things on how this particular company does things and how that updates your model practically. So you really need an integrated system between the neuro and the symbolic. And you can't just take a large language model and a logic system and somehow try to glue them together. That's not going to work. So an interesting perspective that DARPA gave a few years ago is what they call the 3 waves of AI. And what they mean by that, the first wave is basically what many people refer to as good old-fashioned AI, stuff that was done 70s, 80s, 90s, and so on, expert systems, rule-based systems. And so IBM's a Deep Blue would be a good example of that, the world chess champion computer. So that's wave 1. And it got quite a lot of applications, and of course, rules-based systems are still, important in many areas. But then the second wave hit us like a tsunami about, 14 years ago or so, where people figured out how to get neural networks to actually do useful things. That they have massive amounts of data. The large companies like Google and Facebook had massive amounts of data, massive amounts of computing power, and they figured out with a few tweaks how to get neural networks to really do interesting things with deep learning, essentially. And, there were major breakthroughs in the improvements of speech recognition, of translation, of image recognition, and so on. And now more recently, of course, that has gone into generative AI and the really phenomenal performance of these systems. So we are currently on really the focus is on wave 2. Now, what DARPA mean by wave 3 is what is best described, I think, as a cognitive AI as opposed to statistical AI. So cognitive AI starts with the question of what is special in human intelligence. So it starts with understanding human intelligence. As opposed to starting with, hey, we've got a lot of data, we've got a lot of computing power, that's a hammer we've got, what nails can we find? So cognitive AI really goes back to the original thought of building thinking machines, but understanding what is entailed in thinking, and especially in human. And the important things here that it's adaptive and autonomous. So cognitive AI, as I just mentioned, it can learn incrementally and can learn conceptually. So that's a big part of the power of human intelligence is our ability to get a few examples and then to be able to generalize. So that's concept formation and abstract thinking. And humans, what makes human intelligence special is we can form concepts on top of concepts on top of concepts to end up with very abstract concepts like, honor and marriage and government and things like that. So it's that ability to autonomously form these high level concepts. And it's also our metacognition, our ability to reflect on our own thinking and to guide our own thinking appropriately. So to highlight to identify a common confusion is unfortunately a lot of people believe that having a lot of knowledge makes you intelligent. But that's not the core of intelligence. The core of intelligence is the ability to learn and to learn in a conceptual way. So I'm sure you've all come across people who may have a lot of knowledge, but really aren't very good at thinking. So having a lot of knowledge is really not the measure of intelligence. It's the ability to acquire knowledge. And what AI really has been focused on, the sort of narrow AI era that we essentially still in, call it narrow AI or external fixed, is really that the focus has been on how much data, how much knowledge and skills can we acquire, and we don't really care on how it's acquired, as opposed to being able to focus on the ability to acquire it interactively in the right way. And again, having kind of a read-only system, you build a model, and that's fixed. It's essentially read-only, and that the improvements are really initiated externally. We use these models, and then we find they don't quite do what we want them in a particular application, and it's a human external intelligence that then decides, do we need to tweak hyperparameters? Do we need to train it with additional things? Do we need to do prompt engineering? Do we need to have an external database, a RAG or whatever? So it's a human intelligence that's still very much in the loop to actually be able to solve problems. Whereas the AGI way of thinking about things is really that the system can learn by itself to figure these things out by itself, like an intelligent human can. So we ultimately want to get to full uh, adaptability, that the system can change to changing circumstances without having a human in the loop, or with minimal human in the loop. So with the incremental learning ability, the cost of training these systems will also plummet. It'll be orders of magnitude lost. So we're not going to need $7 trillion to get to AGI once we have systems that can actually learn incrementally. And there are other benefits to the approach that I'm talking about, is that they won't hallucinate inherently like large language models do, and they'll have much better understanding and metacognition, and also they are auditable, which are again in this community I think is kind of a big deal. Now, how is that possible? I'll really, for the rest of it, I'll be giving some of the details of how we're going about trying to achieve this kind of low power, high intelligence AGI approach. So the data algorithms, the actual learning algorithms, are similar to our brain. Our brain doesn't have very complex learning algorithms. They really, maybe a few dozen core mechanisms that our brain has. Simplest, the most obvious one is sort of Hebbian learning. Fire together, wire together, but pattern learning and so on. And I'll go through a list of those. It doesn't require backpropagation, so that's an inherent part. Our brain does not use backpropagation to any significant extent. It's knowledge graph based, so there it's much more like a computer than our brain. That we believe by having a vector knowledge graph that encodes all of the knowledge and skills that the system has, including mental skills, is the way to go. So you inherently have something that is scrutable. You can go through the knowledge graph. Now, it may get very complex, and you may need sophisticated tools to follow a complete complex train of thought or how a system acquired a certain belief. But in principle, you can determine why a system. It's not a black box. So I find this graph quite instructive to kind of map out the difference between these two approaches. So on large language models, as I said, the focus is on having a lot of knowledge, having a lot of skills, and it's way off the charts basically compared to what humans know. I mean, what these large language models embody, they could probably tell you the cricket scores of a game played in, I don't know, 2000 between Pakistan and Afghanistan or whatever. Enormous amount of knowledge and these skills that they pick up through this trillions of words that they trained with. But what we really want is we want the ability to learn in real time, adaptively, conceptually. That's really what makes human intelligence possible. So the cognitive AI approach gets us there. Whereas a statistical approach, an analogy would be here, if you want to go north, but you're facing, west, it doesn't matter how fast you go or how far you go, you're not going to get to your destination. So I think it's fundamentally the wrong approach. And another comparison here is, I won't go through these in detail because I've already spoken about that. And if you want to look at them, there'll be a recording of this. Anyway, but it really is like chalk and cheese, the two approaches to AI. So let me talk just a little bit where decision intelligence and rule-based systems fit in once we have AGI, or as we get closer to AGI. These systems will be, I think, very important, crucial tools for an AI to use, because you really do want to have your rules, your business rules, your logic, in many areas, you want them to be very explicit. You want them to be able to have them externalized and not hidden away in some complex model, so that they can be scrutinized. And I can just imagine if procedures, like government procedures, like how you deal with medical insurance or government laws and things like that, even within companies, the more you can have rules and procedures formalized and made explicit, I think the better. You can automate it. You don't have ambiguity, and it's just a much better way of doing business and applying laws. So I see the sort of decision intelligence part of having an external system that's deeply coupled or closely coupled to an AGI, that it can update the rule system, but also interactively use the rule system to make decisions, I think will be incredibly powerful. So if cognitive AI is so promising, so wonderful, why isn't everybody working on it, or who is working on it? And well, it's kind of an accident of history, I think, that statistical systems have been so incredibly successful in so many ways, that all the momentum, all the money that's going in is going into that area while it still seems to be progressing. And so it's really that it's sucked all of the oxygen out of the air. And we can see that if you try to, in fact, one of our employees tried to do a PhD in cognitive AI and he couldn't find a sponsor. So he ended up doing it in statistical systems. You want to get grants, it's going to be statistical. You want to get funding for your startup, statistical. You want to earn the big bucks. You want to get a paper published. It's the only game in town right now, because it has been so spectacularly successful in so many areas. So right now, really, we could only find my own company and two others. Intel have a research project which is very much along the lines of cognitive AI, and a company called Elemental Cognition. David Ferrucci, who actually was one of the key designers of the Jeopardy, Watson Jeopardy system, seems to also have very much the same ideas. And then our own company, Aigo.ai, we actually have alternated between being in development mode, where we crank up the IQ and the capabilities of our system, and then commercializing it. And our commercial version, we had 1-800-Flowers and Harry and David as our customer. And over the last Valentine's Day, we actually replaced 3,000 agents. So that was kind of getting a proof point for our core technology, but commercial applications always push you down the road of sort of narrow AI, doing things for a specific customer, for a specific system, rather than building general AI that can learn. So we actually recently decided to put our commercial on hold to be able to focus 100% on getting our technology to full human level. So I want to talk a little bit about how we see a path to AGI with cognitive AI and cognitive architectures. I think many of you will be familiar with sort of the approach of cognitive architectures. Cognitive architectures have also been around for quite a long time, and they haven't really worked that well. They haven't really taken off, and I believe the reason for that is, apart from they're not getting much oxygen in terms of, they're not getting much love in terms of funding and support. I think there are a couple of inherent, or not inherent limitations, but practical limitations. One of them is that generally they tend to be quite modular, that they're basically like a good engineering approach. You have modules that do different things. But the problem is that these modules really don't work in an integrated fashion. And our own approach to that is basically that we have this backbone of a super high performance vector graph database that serves as the backbone, or infrastructure. And then we have all of the cognitive or learning algorithms that are custom designed for the system, and they're designed to work very, very well together, synergistically together with each other and with the graph database. So our implementation is actually 1,000 times faster than any commercially available graph database. And that's been key for us to actually get a cognitive architecture to work in this way, and having a neurosymbolic cognitive architecture. So we, how far have we got down the road of achieving that? As I say, we have the core technology that has already been commercially validated as well. 6 years ago, we actually had a development prototype demo that we have called an Elder Companion demo. And there's a white paper that explains a little bit more about sort of our path to AGI. Now, an important part, I believe, is not to aim straight away for full human level intelligence, or adult level intelligence, I should say, but to focus on building what one might call seed AGI, where you have an AI that isn't yet at sort of adult level, but you have maybe like a 10-year-old that wouldn't really be very viable commercially for many applications, but as a 10-year-old can already learn by itself to a large extent. And then you have this bootstrapping effect, where the system can largely improve itself and learn by itself, by sort of, think about it, by hitting the books. So our focus is basically, how can we get to that point where the system requires less and less coaching and teaching and external work, and can largely learn by itself, just asking question, asking for help as it goes along. And our approach is to do this on a PC-based assistant, essentially, so it can see what's on your screen, can see mouse movements, can move the mouse and click and have text interface. So the approach there is, I sometimes refer to this, I'll skip for the sake of time, I'll skip this. So I sometimes refer to this as the Helen Hawking theory of AGI. It's basically Helen Keller, who was blind and deaf and ended up basically through sign language becoming very competent and obviously super intelligent. And then Stephen Hawking, who obviously has very limited dexterity, also super intelligent. So the point I'm making here is that you can have limited sense acuity and limited dexterity and still be very smart. So we're not too concerned about the system not having dexterity and full human sense acuity. Now, the last bit, I'll just dive a little bit into our more details of our approach. There's also a white paper that talks about our approach, and basically the idea is that you have perception, you have a grounded system that can learn through what it sees, in our case on the computer screen, and it's from these percepts it can build the concepts, and from concepts it can build higher and higher level concepts. Now, not everything is learned perceptually. We also, as humans, we don't. Once we have enough grounding of core concepts, we can basically bootstrap on that and learn more and more. The actual, I mentioned our approach is to have a very limited number of relatively primitive cognitive algorithms, and akin to the brain. And some of these core learning and reasoning algorithms, or cognitive algorithms, are pattern recognition and generalization, being able to form associations, the certain amount of reinforcement learning, activation spreading that the system has. So as you think of one concept, it automatically associates other related concepts to that. So there's an interplay of these, few dozen core mechanisms that allow the system to learn interactively and to learn language and to learn reasoning. And the actual data structures in there, they're all vectors that are encoded, and they're basically different kind of vectors depending on whether you're encoding some static information, dynamic information, dynamic patterns and abstractions, relationships, and so on. So there are, again, a dozen or a few dozen different types of vectors that really cover the whole spectrum. So you don't create new vectors for every concept that you have. They're just different classes of vectors that work in a slightly, or operated on in a slightly different way. Just for interest's sake, for anybody wanting to work on AGI, just kind of quickly go through the path. I started off by taking off 5 years to actually study intelligence from perspective of philosophy, epistemology, theory of knowledge. How do we know anything? How can we be certain of things? I studied cognitive psychology. How do children learn? What do IQ tests measure? How does our intelligence differ from animals, and so on? So, and then of course I studied computer science, and that really was the foundation of all the work that we've done over the years. As you can see there, sort of, V1 is where we started. V2 was sort of our first AGI, early AGI prototype, and then we commercialized that in a call center automation company called Smart Action. That company was sold. We then went back to development, V5, commercialized that, V7, and current company, Aigo.ai. And we basically now at what we call V9, where we back into developing and cranking up the core technology. And the idea is, as I said, to now go from 3-year-old, 4-year-old, 10-year-old to a point where the system can actually hit the books, learn by itself, and take on a job. Now, the reason I also wanted to highlight this is anybody working on this. I've seen over and over again people fall into what I call the narrow AI trap. Is basically as soon as you try to beat some benchmark or have some impressive thing you can publish or to commercialize, you're basically going away from pursuing the core learning abilities, and that you end up putting external intelligence to hard code things and just to get things done quicker or better. And there's tremendous pressure, from investors, or if you're an academic, from publishing results that beat some benchmark or something. And then it's the external intelligence that really achieves the results rather than the core. And as I say, I've seen that again and again. And so it's really hard to continue pursuing the core problems of a system that's not going to be very impressive in the early days and not going to beat any benchmarks. And one specific example is, for our commercial system, we ended up putting a lot of manually created rules. There were many thousands of rules for language understanding, pragmatics, and business rules for reasoning ability. So we had a lot of rules. So the green part is basically the graph database of what the system learned interactively, and the yellow part there is what rules that we manually coded in. And then there was also quite a bit of code that achieved certain of the reasoning and language ability. Now, the new approach is that basically there will be no rules, no human crafted rules at all in the system. It basically needs to learn everything that it knows and have much less of a code base. So again, the idea is that the system learns most of the abilities. So like nature, nurture. So the nature part is the orange part in code, and the nurture part, what it can learn, is the green part. So I've already spoken to about that, but I just want to get back to how we actually do that. It's basically the focus is on the curriculum, and about half of our staff are actually what we call AI psychologists. So it's people who understand the mind of the AI and how to teach the AI and putting it through a curriculum and through the learning exercise. So we are basically we've got the core, the level one, the core knowledge encoding and so on, that we've got up and running, and we are now very much working on level 2, is to get to the natural language and reasoning ability of a 3-year-old, so that we can actually demonstrate this core learning ability to people. And then we want to expand our team and more rapidly get to 10-year-old level. And by that time, it'll become very obvious that basically we have a way to AGI. And we believe this can happen in 2 years, given the right amount of funding. So why don't we have AGI yet if it's so beneficial? As I said, large language model statistical systems have really sucked all of the oxygen out of air. So that's one reason. If large language models are not going to get us to AGI, then that's kind of, a distraction, a detour, an off-ramp. And even of all the people working on AGI, when they claim to work on AGI, large companies, do they actually have a specific roadmap? And the answer is no, because they say there are still major breakthroughs required. They don't know how to solve these problems, apart from the absurd amount of training data and power required in that approach. There's also an interesting thing that I've discovered over the years is there are actually very few people who are comfortable to think about the problem from a cognitive psychology point of view and philosophy. Cognitive science used to be a bigger thing, 20, 25 years ago, where you really have the intersection between philosophy, cognitive psychology, and computer science. now the focus really, and the people rising to the top and getting paid and trained are really trained as mathematicians, logicians, statisticians, much more. So even when you start asking the question, well, what do you need for human level intelligence? What's important? It's not the sort of not something they're interested in. They're not interested or knowledgeable in how the mind works and how humans learn and what's important, like concept formation and so on. So that is also, I think, a big handicap. I actually have an article on that. So I'd like to. I really believe AGI is super beneficial for humans. And of course, that's a whole nother debate on what the risks and benefits are. But I think the benefits totally outweigh whatever risks there are. And I believe the risks are minimal. So anybody who's interested in helping make this happen, I think we're at a unique moment in history where we've had a taste of AGI with these large language models. They seem so close in some ways and yet so far in others. So imagine instead of spending trillions on building bigger data centers and nuclear power plants and whatever, we could actually focus on making this technology happen, focusing on AGI in a much more reasonable way, closer to the way the human level works. So I'd like to invite anybody who's interested in making that happen to contact me and see how we can work together to accelerate getting to AGI. So that is all. Thank you.
Thank you very much, Peter. Very, very interesting. And we open for questions. Please just unmute yourself and speak. Helmut?
Yeah, just one point of data that might be of interest from Ireland. In 22, 18% of the electricity used in Ireland was used for data centers. It's foreseen that within 2 years it may be over 30%. I think it's obvious that this is not the way we can go forward. Eventually, we'll just have data centers sucking up all the energy on the planet. So I think your approach that you mentioned with a lot less energy consumption and a lot more localized use of data is definitely what is needed.
Yeah, absolutely.
Okay, thank you. More questions? Okay, I'm sure people have more questions. In this case, I would ask Peter a question. Approximately 15 years ago, you made presentation in similar gathering at DecisionCAMP, and that time it was a hot topic was statistical machine learning for translation. And you spoke, it's kind of similar situation because Google was extremely successful and everybody loved Google translators. And Peter Norvig did very interesting description of this. And you mentioned that time that Google about to hit a wall with a statistical approach. And actually it happened, but in the real world, everybody using translators right now, and it's quite practical, right? So similarly, we can see that even statistical approach can solve some relatively simple logical problems, and we have this in our DM community challenges. We can see it, but sometimes it's absolutely out of. It's not just hallucinate; it produces wrong decisions, and everything what you mentioned is right. So, do you see this analogy and the statistical translation?
Oh yes. It's just these systems are with big data, having massive amounts of data. It's just we can't wrap our head around what you could do with tens of trillions pieces of information, training data, or it's really quite phenomenal. But they simply they are hitting a wall in some ways. The technology translation is still not human level. And in fact, in our commercial side, we used state-of-the-art Whisper. We had our own speech recognition system that we had developed that was very good. And then Whisper came out, and it was better than anything we'd been able to do. But then as we started working with Whisper, we also very quickly found out its limitations, and it's nowhere near human level. It simply isn't. It doesn't have that context of a human. We know what to expect. We understand the topic, and we can disambiguate and so on. We can adjust on the fly to different accents and so on. And these systems simply cannot do that. So yes, I think statistics can get us that far, but there's, they're not dynamic, and there's this long tail. I also have a Tesla, self-driving, and I love the car, and I think it's amazing. But you have these edge cases; it just simply doesn't have the common sense. It doesn't know how to deal with them, and you simply cannot acquire enough knowledge. You can't collect enough data to do that. And then the other thing is, again, being adaptive. For example, if you move into a new neighborhood, you may learn as you drive around the corner, there's a blind driveway where, people reverse out of it. So, you're just more cautious next time. Now, systems built statistically cannot learn that kind of stuff on the fly, you know.
Any more questions? Okay, Lynn, go ahead.
So Peter, thank you so much for this. And my question is relative to what you all just talked about. How can we take advantage of the practical uses of these systems that are in place that can help us today, and yet market and help people understand there's another level coming, and not to lose sight of that? How do we deal with that messaging out to our executives and our investors and that sort of thing?
It's hard. I mean, that's what we're trying to do is, there is actually a lot of unlearning that has to happen. If people have spent their whole careers on statistical systems, to then talk about, the starting from first principles of what intelligence requires, they just sort of, their eyes glaze over. Usually it's sort of, whoa, this is not something I really can relate to at all. And it seems incredible that with all this massive amount of money being thrown at statistical systems, that there should be an approach, that, well, isn't that obvious? So, I'm doing a lot of podcasts and things, and I'd welcome other people. I'd hope other people would also start to spread the message that there is a better way.
What if we came up with, what I understand from communicators is that story reduces cognitive resistance, right? And what if, because talking to the practitioners is probably not who we need to be talking to, right? Isn't it the executives and the investors who don't really understand this at a practitioner level, right? I mean, building that story that we all could help you, get out there. Maybe we need some fine art students or somebody like that to help us with that.
I'd love it if you can help us do that. Yes, absolutely. I totally agree. If we could tell the story in a way that makes it accessible, that'll be terrific. So please, anybody who has ideas, contact me, and that's very much what we're trying to do, is this education.
I will get with you afterwards via email.
Thank you,
Cool.
Lynn. Yeah,
All
Peter at Aigo.ai.
I wrote it down. I got it.
Okay.
Okay.
All right.
Thank you.
Yes, thank you. And Peter, hopefully you will stay for our panel at the
Yes.
end of the day, so people will be able to ask more questions. Because I'm sure people just understand that they don't want to open a huge discussion, but everything what you described deserves large discussions, and I really appreciate what you did. And I just want to make one comment, that we need to bring younger people, because if you look, we're both bold, and we have so many people older who devoted their life to similar topics, and we need to bring young people And unfortunately, if you look back, for example, another person who devoted his life, Doug Leonard, creator
Yes.
of Psych, we lost him recently, and he was our presenter, by the way, too, in DecisionCAMP before. And I hope that we need to find a way to bring more people through universities, through other activities. So thank you very much for inviting presentation, Peter.
Yes, well, thank you very much. And yes, I'll be at the panel as well, panel discussion. Thanks.